Let's jump to the next topic, which is spectrum analysis. Once I get, the information from the spectrum, what do I have to do? As I'm writing here, it's a delicate process because the classification process and deciding if there is an opportunity for transmission or not is extremely dependent on in which domain you are observing. Because from this spectrum, from this information taken from the spectrum, we extract features. These features can be anything. It's a basic processing. You decide which is a relevant feature for the goal you want to achieve. But so the first question you have to ask yourself when designing the system is, what do I want to detect? Just the transmission opportunity? Who is occupying the signal, the spectrum? Or which type of modulation is the guy using for occupying the spectrum? Or what else? Up to your creativity and fantasy and needs to decide it. But you have to ask yourself, because based on this, you can decide which is the proper feature you need to extract from the spectrum in order to have the proper classification goal. Again, these are possibilities that we have about types of decisions. These are the most common, but you can decide whatever else you want. Combination of them doesn't matter. While the spectrum walls is really, the first cognitive radio idea, the rest was kind of imported into cognitive radio from the military world, from a field called a signal interception, which is a fairly old field. We are talking about something that is started in the Second World War, and the first interesting papers are from the 60s and then 80s.
Okay, so you're talking about detection of the system type of primary user.
Yes.
And then detection of air interface type and signal characteristics. So what is the constitutes the system type?
The system type you can, for example, detect if it is Wi-Fi or if it is LTE.
Yeah, but you can also detect that the type of the, here it says detection of air interface type and other characteristics.
You can, they seem the same, but they are not.
Okay.
Because each of them requires a different type of information to the classifier to take the proper decision. Because if you just need to decide the type of system, for example, Wi-Fi has, the Wi-Fi signal has a certain signal characteristics, and LTE has another one. You extract one feature, it will be clearer later on. One feature is maybe enough. But if you want to detect the modulation that air interface is using, that feature is not enough anymore. So you need to change the amount and the type of information that you are feeding into your classification system in order to take the proper decision. I put them in the increasing order of complexity because if you look at it, spectrum walls, it's a binary decision. And spectrum walls, you can do it with a very, very simple feature that requires basic processing. I will show you later on. The system types require a bit more. But if you don't want to dive into the characteristic of the signal, maybe with a bit more of processing than this one, you can get it.
Because I'm just wondering, do we really need that?
It depends on your application.
Okay. Also, how you detect what is the primary and what is the secondary user who is already there?
That's what your application again. It's up to you. I am just trying to give you an idea on how to do it, but the classification goal is related to the application. Not everyone is tackling the same application, because if you want to know who is the primary and who is the secondary, chances are that the two systems are different, right? And if you want to know who is if the primary is transmitting, you need, for example, this one. But instead, if you want to have more complex transmission and you want to adapt your modulation encoding scheme according to the modulation encoding scheme of the other guy, in order not to disrupt his transmission and not lower too much the quality, or to find the proper orthogonal code given the orthogonal code of the other guy, then you need to dive in. And the amount of information required is totally different. I don't want to spoil myself. I'm replying vaguely because I don't want to spoil the rest of the lecture. But the idea is to try to give you some ideas about how to deal with all of them. Not only not only about these general things. Going forward, let's start from the basic. And the basic goes back to 1967. This is the most simple methodology that is still used in cognitive radio. You still see papers that use it. And it's energy detection. Do I need to spend too much time on it?
No, there are papers.
No, okay. You have papers there, and I try to put, the old one from Wurkowitz, the original one, where this formula is extracted from. But also a couple of new papers that are using this methodology. The latest one is from a colleague and a friend, Andrea Giorgetti, and they are using energy detection and they are improving it, doing noise power estimation, because now the problem is also detecting in real time, which is the real noise power, because we cannot assume anymore that is, same amount. We take the 27 degrees Celsius as a ground floor of operation, and if we want to be precise. If we want to be precise on the classification we have, we need to be precise also on how much noise we really have, especially now that we have available low noise components. Why it's still used? It's written there, but you can imagine easily, because it's very simple. Everyone does it. It's embedded everywhere. Basically, any RF board has almost always embedded a bolometer, which is an analog energy detector. If there is energy, you have this increase in interference temperature, as it's called. And it generates a very, very low processing load when you use it as a feature, because generally you define a bandwidth, you decide the granularity, and then once you have the information about the energy in this bandwidth, you decide if, for example, the channel is occupied or not. That's how Wi-Fi does it. Your Wi-Fi does this one exactly. And for spectrum walls, could be good enough. I want to detect if I have an opportunity or not. Let's assume a reasonable threshold for saying that the channel is free. If I see an energy which is below the threshold, the channel is free, let's use it. Classification, It's basically a pressure comparison, one if-else rules, and that's it. Done. We have our cognitive radio. Not really. And clear channel assessment. Nothing new under the sun. It has been there for the last 20 years. But people are still using it. And that's why I'm presenting it to you, because it's still considered fundamental for cognitive radio. And interference temperature, as I was mentioning before, and you were mentioning before, it's another metric that they were considering a bit more scientific than simple energy detection. That stopped being used after, I would say, 2007. I haven't heard any more papers that use interference temperature lately.
Because I think that FCC has made the definition of the interference temperature. I'm not sure.
Yeah, that's the definition from Paul Colozzi, and Paul Colozzi is one of the main consultants for FCC. So that's the FCC definition, basically. And substantially what we say is that, okay, you get some power, and you basically go and measure which is the equivalent temperature that is related to the power that you are receiving from the RF. And this equivalent temperature, it's not a real temperature, of course, but if you use the same type of conversion that you use for noise between temperature and power, then you have a temperature increase between the noise temperature and the signal temperature. Why using it instead of using the power straight ahead? I don't know, to be honest, but because you are also passing to the Boltzmann constant, which it's not exactly comfortable to process in hardware, because so Hyken of course mentioned it in an overview paper, but to be honest, no one uses it anymore. It's just another way of seeing the same thing as before. Maybe because they were using in a regulatory framework, I don't know. But that's what was there, and that's why I'm trying to present it to you, because that's part of the history, fortunately I would say, because no one they decided that once they have the power, it's good enough. That's another interesting feature that I used it in the past, and it's basically a very, very simple version of the following what I will present, but the principle is very, very simple. And it is basically that you consider the spectrum of the signal as, the power spectral density of the signal, you consider it as any common statistical distribution. And you treat it as it is. And from this, distribution, you get the cumulants. Nice and easy. Why? For example, it's very easy to distinguish between different types of modulation, air interface types, CCK versus FDM. It's very, very simple to do it, because they have different statistics. Going a bit more in detail, you take the PSD, you normalize it respect to the total energy of the signal, within a certain bandwidth, of course, and then you compute the cumulants. The average gives you what we call the center frequency, more or less. The standard deviation gives you the half bandwidth, and of course you can derive the total bandwidth of the signal. The skewness, which is the third order cumulant, gives you an indication about the asymmetries of the distribution, if it is left-centered or right-centered, where is the center compared to the, sorry, not the center, the peak compared to the center of the signal, of the signal of the bandwidth. And finally, the kurtosis, which is an extremely interesting feature, because it gives you an idea of the peakedness. And the peaked, yes, how many peaks the distribution has. And it's useful if you want to classify, for example, a single carrier modulation versus UFDM, because the UFDM has multiple carriers, while a single carrier modulation has one. And these are the formulas. It's nothing, again, nothing new under the sun. Here it's one paper. I know it's very, very bad to present my paper as a reference, but it's, I did a work and I proved that the kurtosis is a discriminant feature. So it's possible to extend this cumulant theory in two ways. If instead of considering just the spectrum domain, I consider jointly the time and frequency domain at the same time, and still using the cumulants. Usually it's used the standard, no more than the standard deviation or the average. It's possible to do it in two ways. In a more restricted way, which is the cyclostationary features, I will tell you what they are in a while, or the full time frequency distributions. You probably have seen time frequency distributions several times when looking at the music spectrum or something like that. And in both cases, you extract cumulants. You never use them as they are because they are functions, basically. Let's start from the cyclostationary. Why? Because they are widely used and widely considered. For example, there was a project where Nokia implemented in a mobile phone a cyclostationary feature detector. So they did it, it's real, it's getting close. It's not the simplest thing in the world, but it's possible to do it. And it's very simple. The computational complexity is not too high. It's not as simple as the previous one, but it's not too high. And it's basically an autocorrelation function where you consider one single frequency alpha, given a certain signal, x, function of tau, which is the autocorrelation. There is a problem. Since the fact that this autocorrelation function, where you can see that it's an autocorrelation because you are cross-correlating the signal with its own complex conjugate version extended to a certain time interval. The problem is that you do it for each frequency you want to detect. Why? Because when you transmit wireless signals, sometimes, actually often, there are cyclic components. If you take a normal single carrier modulation, the only repeated or cyclic frequency, in the sense that it's always there, it's just the carrier. In OFDM, you have a multiple set of carriers, but some of them could be moved up and down, especially in UFDMA, where you have multiple users and the power it's variable and so on. So it's very, very difficult to pick up the right frequency you want to detect. Nevertheless, these type of features help you identifying certain types of signals and help you, and as Louis, I hope, will show you, defining actively a fingerprint to embed in your wireless signal that it's possible to detect with a cyclostationary based detector. And that's how we do frequency rendezvous, for example. Mm-hmm. If you want to do blind detection of all the cyclic frequencies, so the frequency which is always there, in a wideband, forget it. Because doing blind detection with extracting this type of feature means that with a certain frequency granularity, you need to repeat the same thing hundreds of times. Computationally, computationally it's very expensive and it's not worth the effort because you can have more synthetic representation of what you're looking for. If we want to extend it in a more general framework, we can consider a representation of the signal not only in time domain, but also in the frequency domain at the same time. So this has become relevant when the signal has kind of weird dynamics. The example I put here is Bluetooth. Do you know how Bluetooth works? Any idea?
You switch on the Bluetooth and you see on the computer that.
Yes, okay, that's yes. At the physical layer, Bluetooth is a frequency hopping system. So it has 1 MHz wide carriers that jump with a pattern of 1 MHz, basically. They have 92 frequencies you can jump from, and according to your frequency pattern, because they are several and they are try to be orthogonal as much as possible, you jump periodically from one frequency to the other, up and down. That's how it works. If you take a snapshot, you see an Aalborg blend signal. If you take a long snapshot in time, what you see is something that looks like an OFDM signal with a subcarrier spacing of 1 MHz. Is it helpful for defining that there is Bluetooth? No, not at all. And if you look at only one single snapshot in one pattern only, you see one carrier frequency which is 1 MHz wide. Is it Bluetooth? Is it a spurious? Maybe. What is it? I don't know. So, in that case, can become handy a time frequency distribution. The simplest one is the short time Fourier transform, which is basically you perform an FFT on the signal, or IFFT if you are try to receive no, that's in the case of the FDM. You take an FFT, and then you repeat the operation several times. And then you get a time frequency matrix. Frequency and time. It's not the most accurate possible because you have phase gaps, because between one snapshot and the other there's no continuity. So the function is not mathematically the most beautiful possible. Very simple to do, you can do it immediately, but it's not the best. You would need something a bit more to have something mathematically tractable that has very nice properties and that you are sure that it works. For example, one of the several is the Wigner-Ville, which is extracted by using the distribution theory. So this is not a function, it's a distribution. There are very, very subtle differences on how you define the domain of the function itself. But instead of using the Riemann's definition of integral, you need to use the Lebesgue one. I don't want to enter the mathematical detail because, again, I'm not a mathematician and you would have very bad or wrong explanations. And from this one, you need to extract cumulants as well, because that's a function. As you can see, the function looks like, basically, it's exactly the same as the previous one, as the cyclostationary one, because it's, again, an autocorrelation. This time, theoretically, you should go minus infinite, plus infinite, of the signal versus its own complex conjugate to the phase. The only difference is that omega, that in this case is the pulsation and not the frequency, it's a function, it's a variable of the function, of the distribution. So instead of being outside here, it's inside the parentheses. This gives a complete representation of, in time and frequency, of the signal. And it's smooth. mathematically speaking. Here you can find, again, some examples. Again, it's very bad giving my papers as a reference, but that was the one that I had handy. There are others that use the same. Just need to check the literature. With this one, we managed to identify Bluetooth versus wireless LAN. So, and we also managed to identify if they were combined or overlapped one on another.